Hey, chemistry team, you ready for video number 8, the last one for chapter 18? I'm not going to cover some of the later sections in this chapter. Um, we won't be doing it in lab, so read it if you want to have some fun, but not necessary. So we're going to be looking at, now that we've seen the effects of adding acid and complex, ligands and those kinds of things, common ions to solid solubility, can we control and manipulate the solubility of a solid? Like, could we even prevent one from forming? Remember QSP versus KSP. If Q is greater than K, we get to precipitate. If it's less than K, you don't get to precipitate, right? The criteria for precipitates. So if we know the concentration it takes to get a precipitate, if that's dependent at all on the pH, either the hydronium or the hydroxide ion concentration, we can manipulate those concentrations to maintain the ion concentrations below a level necessary for precipitation. Oh, it requires some quantitative gymnastics to do it, but you could do it. So if the hydroxide ion is involved at all, either directly in the equilibrium expression from the equilibrium equation or indirectly through, ammonia or a weak base producing OH minus, right? We can control that. Using buffers, we can control the pH and the OH minus concentration. If that's involved at all, a couple things we can do, right? If we're given, you'll commonly see two types of problems. If you're given a pH, right, maybe a buffer is holding the pH constant at some level. From that pH, you could calculate the OH minus and H3O plus concentrations. Commonly, you're interested in the OH minus because we're not going to form a precipitate with the hydronium ion, right? But we can form lots of them with OH minus directly or indirectly, okay? And then given that, we could, if we know the pH, we could calculate solid solubilities. We could tell whether precipitates are going to form or whether they won't form, right? Those kinds of questions. And we could solve for the pH. Say we're not given the pH. Say we're given the solubility. We could say, well, what pH is required to give a solid a particular solubility, right? So create a buffer. You could create that buffer solution with that pH, and that will give a solid a particular solubility. Remember, in pure water, it has a certain solubility. You could adjust that, right? If its anion is dependent on acidity. So we can use a buffer to adjust its solubility up or down if you want. Well, probably down, but or we can say what pH is necessary to form a specific precipitate, right? What's the minimum hydroxide ion concentration we need to form that precipitate? Or vice versa, what's the maximum value of OH minus we can have to not get a precipitate, right? Anything above that, we get a precipitate. Anything below that, we won't. Several types of questions. Let's just do one of them and see how that goes. Let me stick a problem up on the board. Here's an example problem, a type of problem. They're all kind of similar. I could throw things around a little bit, probably 3-4 different types of problems, but they all sort of involve what's the hydroxide ion concentration and how does that impact the cation's concentration. All right, so this one, what is the solubility of a particular solid in a solution that's buffered to a particular pH? Very common. Or vice versa, right? I could flip that around and give you the solubility. What's the pH? Same kind of idea. All right. So in this case, we're doing magnesium hydroxide. Pretty obvious. That's got OH minus in it as the anion. So this is going to be sensitive to the pH of the solution. That's going to really impact its solubility. Well, let's do some quantitative calculations this time. We didn't do that before. So what's the solubility? And remember, solubility is grams of the solid per liter of solution. Molar solubility is moles of solute per liter solution. So what's the solubility of magnesium hydroxide solid in a buffer solution maintaining a pH of 9.62? So this is in the basic range, right? It's above 7. So let's see. Let's just put the steps down to get our thinking process right. What's the first thing we're going to do? We're really only given a couple things, and I'm going to pause this because here comes the helicopter. Coast is clear. I think that might have been the social distancing police. Keep a distance of 6 feet, please, everybody. 6 feet. All right, except for my cats. I don't have to social distance for my cats. Yay! What are we going to do to solve this problem? I look at this problem, so say I'm freaking out on an exam. I've got a pH and I've got a solid. Well, I know if I have a solid, I can set up an equilibrium equation and an equilibrium expression. Yay! Don't have to think. Please, can I have 2 points out of 10? Right? Something like that. Give me something. Don't leave it blank. I got a pH. If I know the pH, that's negative log hydronium, right? So I could solve for the hydronium ion concentration from that pH. And if I know the hydronium ion concentration, I could solve for the hydroxide ion concentration. Or vice versa. If I know the pH, I could subtract that from 14 to get the pOH. If I know the pOH, which is negative log OH minus, I could solve for the hydroxide ion concentration. Net effect, what's the hydroxide ion concentration from the pH? Remember back in chapter 15 or 16, I reviewed pH, pOH, H0 plus, and OH minus, the square. You can't go diagonal, but you could go over and down or over and up. 2 ways to do that. Whatever you got to do, however you do it, get the hydroxide ion concentration. And then set up the equilibrium equation and equilibrium expression. And we'll know the KSP value. We'll know the OH minus concentration. We'll be able to solve for the cation. In this case, it's magnesium. It doesn't matter what the cation is, whether it's aluminum or zinc or cadmium. Who cares what it is? It's the same thing. We'll solve for that cation concentration. In this case, what's the magnesium ion concentration in that buffer solution at a pH of 9.62? Right. Well, once I know that, that's my solubility, X. If you look at your ice table, that's X. Okay, because it's in a 1-to-1 mole ratio with magnesium hydroxide. So I can take the moles per liter of the magnesium ion, convert moles of magnesium ion to moles of magnesium hydroxide, 1-to-1 mole ratio, and then convert moles of magnesium hydroxide to grams of magnesium hydroxide using the molar mass. That gives me the solubility in grams per liter. So if you don't remember that, you can look back at one of the prior videos. I think it's the second or third one, something like that, where we calculate solubilities or use solubilities. Calculate solubilities given KSPs or calculate KSPs given solubilities. Good review for that. So go ahead, try this, pause it, do step 1, do step 2, do step 3. You can kind of blend 1 and 2 if you want. You could set up the equilibrium equation and expression first and realize, oh, I need the OH minus concentration. And then you can solve for that second. Doesn't matter, but this is a good sequential way of thinking. Pop it out. I'm going to erase this and go do this problem. How's step 1 going so far? We'll just take it one at a time. I'll do step 1, pause it for you, do step 2, pause it for you, do step 3. If you're having trouble eating the whole meal at one time, let's just start with dessert and then go to our vegetables and then to our main meal. I don't know what order you eat your dinner in. Or if you're at a buffet or something. Let's start with the pie or the sushi. I'll start with the sushi. Here we go. We're given a pH of 9.62, and we know that pH plus pOH equals 14.00. That I would give you on a test. All right. Let's solve for pOH and then for OH minus. So obviously pOH will be 14.00 minus the pH. So let's write that down. So pOH will be 14. And some people just do 14.0. Some people just say 14, call it exact. Whatever. Minus the pH. So that'll be 14 minus 9.62. Very rarely will you see pHs and pOHs more than 2 decimal places. Most pH meters will read pHs to 2 decimal places. I know ours does in our lab. So 14.00, you don't have to worry about it being exact or not exact, not important. 2 decimals, right? So what do you go to? 4.38. So that's our pOH. And I know from this equation, pOH is negative log of the hydroxide ion. So good review, that one video from early chapter 16 with the pH review and the pH squared. So my OH minus will be 10 to the negative pOH. So OH minus will be 10 to the neg. Move the negative sign over, do 10 to the X on both sides to isolate out the hydroxide ion concentration. Bringing back some good or very bad memories for you. All right, so 10 to the negative 4.38. Now remember, when you take a logarithm, if you take the logarithm of something, the number of sig figs in that value is the number of decimal places in your answer. Well, it's inversed when you do e to the x or 10 to the x. So the number of decimal places in the value of the x, 10 to the x or e to the x, that'll be the number of sig figs. So see how we have 2 decimal places there? The 0.38, we'll have 2 sig figs in our answer. So pop this out on your calculator. See what you get. 4.168 times 10 to the minus 5. So 2 decimals gives us 2 sig figs. So there's my 2 sig figs. 4.168 times 10 to the minus 5th molar. That is my hydroxide ion concentration. You can always get that from the pH. And again, you could have solved for the hydronium from the hydroxide first, right? And then you could, you could have solved, yeah, exactly. So you could take the pH and got the hydronium ion concentration, and from hydronium ion gone to hydroxide ion using Kw. I don't usually do it that way, but it works. However you do it, doesn't really matter. So that's step 1. So now let's go to step 2. Let's write the equilibrium equation and equilibrium expression for our magnesium hydroxide solid, or whatever solid it is. It doesn't matter. So we've got magnesium hydroxide solid. This should be pretty easy. That's going to be maintaining an equilibrium with its cation and anion in solution. So that'll be the magnesium ion, which is an alkaline earth metal with a +2. And we've got a subscript of 2 on our hydroxide, so we will get 2 of our trusty-dusty hydroxides. So obviously adding acid to this will drop that, shift it over to the right. So we can manipulate the solubility by manipulating the pH of this. Very useful. Here we go. So let's set up our equilibrium expression. KSP will be the concentration of our products raised to the power of their stoichiometric coefficients, right? Would you agree that we can look up the KSP value on our KSP table? Yes. We know the hydroxide ion concentration. We just solve for it. Then we can solve for the magnesium ion concentration. Right? That's X in your ice table, and that will get us to our solubility. So let's do that. Let's isolate the magnesium. So the magnesium ion concentration in that buffered solution with that solid in equilibrium with its ions will be the KSP value divided by the hydroxide ion concentration squared. All right, let's get our trusty KSP table. Let's look for magnesium hydroxide. Lead, magnesium, I can't see upside down. Is that manganese or magnesium? That's amazing. Yeah, a lot of people, warning, red alert, a lot of people will do manganese instead of magnesium and get those backwards. Manganese is not magnesium. All right, we want magnesium hydroxide, not manganese. Magnesium hydroxide. Right there, 1.8 times 10 to the minus 11. 1.8 times 10 to the minus 11. Good to 2 significant figures. I almost did the manganese. Like I said, I was looking upside down. I'm like, hard to tell. I don't have my glasses on. We know the OH minus concentration, 4.1, vertical dash line 6.8 times 10 to the minus 5th. Don't forget to square your OH minus. Everything has 2 significant figures everywhere. So I get 0.010. There's my 2 sig figs. Remember, leading zeros aren't significant. 0.01036 molar. That is your magnesium ion concentration in that buffer solution. Right? So if you control the pH of the buffer solution, you can manipulate the magnesium ion concentration. Manipulation. And from that, we got one more step. Let's do the solubility. Let me erase my board. Let's bang this puppy out. We're good. All right. So I cleared up some space on my board. I rewrote the magnesium ion concentration we solved for in that buffer solution, 0.01036 molar, good to 2 sig figs. And I rewrote that. I took the capital N of molarity and wrote out what it is, moles of magnesium ion per liter of solution. This allows us to use stoichiometry and dimensional analysis, right? Set up a unit line equation and convert moles of magnesium to moles of the magnesium hydroxide. So the solubility, let's rewrite that back down. 0.01036 moles of the magnesium ion per liter of solution, right? Let's convert moles of magnesium to moles of the solid, MgOH2. And then hopefully you can see 1 mole of magnesium hydroxide produces 1 mole of magnesium. Look back at your equilibrium equation. So that is a 1 to 1 mole ratio. And so I can cancel out moles of magnesium, right? Uniline equation. Cancel those puppies out. One of the first things you learn in first semester general chem. Now that would give me, if I stopped here, that would give me the molar solubility of magnesium hydroxide in this buffer solution. But I asked for solubility, so I got to convert the moles to grams. So look up the molar mass of magnesium hydroxide, look up the value of magnesium, add 2 times the value of oxygen. What's magnesium? 24.305 or something like that, depending on the periodic table you use. Oxygen, 15.9994 times 2, plus hydrogen, 1.00794, the James Bond. Right, 1.00794 times 2, add them all together. Magnesium, the one that I use, has 3 decimal places. Oxygen and hydrogen are more than 3 decimal places. So we're limited because we're adding to the limited by the fewest decimal places in this case, or largest absolute uncertainty, depending how you look at it. So we'd be good to 3 decimal places. So add those all together, see if you get what I got, 58.31968.31968 grams. I ran out of room to write magnesium hydroxide there per mole of magnesium hydroxide. Boop, squish factor. So moles magnesium hydroxide goes bye-bye. I am left with grams of the solid per liter of solution. I got 2 significant digits to start. This is an exact ratio, mole ratio here. I got 5 significant digits in my molar mass. Very rare for a molar mass to limit your sig figs. Very, very rare, but possible. All right, I get 0 points. Pretty. It's kind of weird. We're so used to really big and really small numbers. 10 to the minus 10, 10 to the 14th. When we get a number close to 1, we kind of just go, it doesn't, you can get any number. You don't know, right? So I get 0.60. Again, that leading 0 does not count as significant. So the 0.60 are my 2 sig figs, 41 grams per liter. So 0.6041 grams per liter, good to 2 significant figures. That's closer to 0.60 than 0.61, right? That's got to be bigger than 5 to round up. So that stays as 0.60 grams per liter, or grams times liters to the -1 power. I write them both ways so that you get comfortable seeing both ways, because this is easier to write. If I'm trying to write a test or something in Microsoft Word, I can do it in 1 line, whereas here it sucks up 2 lines. Okay? So some people prefer grams over liters. Some people prefer grams times liters to the -1. Try not to do grams / liters, because then you lose track of the numerator versus the denominator when you do the slash, and that can mess up unit line equations if you end up doing that down the road. All right, so that's how much magnesium hydroxide should dissolve per liter of this particular buffer solution. And if you don't like that in the real world, you can adjust the pH around, and that'll change your solubility. Or I could say, hey, what pH buffer do we need to provide a solubility of 0.60 grams per liter for magnesium hydroxide? And you just work it backwards, and you would solve for the pH, solve for the OH minus, get the POH, right? Subtract that from 14, you'd get the pH. So same type of problem. We're done with this chapter, gang. Woohoo! We're going to a whole new world next. Thermodynamics. No!